now that you have the idea what is how you can do reinforcement learning using function approximation, let's do one example. And in this particular example, what we want to do, we want to get back to the tabular reinforcement learning in this new context, this new framework. So as I told you before, tabular reinforcement learning that we used to do is basically this same general framework with only special case. So the special case is that we are using tokenization for the future representation. And by tokenization, I simply mean this one, right? So it means that for every single state, to represent that, I just use its corresponding one-hot vector, right? So obviously, what you can see is that this is not an efficient representation, especially when I have my state continuous, right? Because there is no one-hot representation of a continuous state, right? Continuous state could have infinite number of cases, right? So then you need to quantize and things like that. But this is not the best representation you can make for your state. But this is what we do in the tabular reinforcement learning. That's the first thing. The second thing is that you are using a linear model. And what do I mean by a linear model? I simply mean that you have a bunch of weights, and your input representation is a vector, so the number of weights that you have are exactly same as the number of entries you have in your state vector, right? And they get multiplied, added up, right? Now, do you have any idea? First of all, say I have n different possible states. How many weights do I have? Say I have 100 possible states. In dummy grid world, we have 4 different states. Or in a grid world, 10 by 10, we have 100 different states, right? 100 different cells. How many weights do I have? Yes? Sorry? 100 again, right? Exactly. So I'm going to have 100 different weights, right? So I have 100 different states. I'm going to have 100 different weights. What is every single weight showing in that case? Just let's do it together. Yes, go ahead. Sorry, no, every single weight. Sorry. Once again, sorry. Not only active, but it gets multiplied, right? It's actually showing you the weight itself. Value itself, but I'm going to show you. OK, so let's consider this case. So say I am in one particular state Sn, right? So this is one of the possible states. Now, my model, which is VW, that linear model, is going to get this weight multiplied with one hot vector, right? Correct? Now, that one hot vector is 0 everywhere. It's only 1 when your state is Sn, right? At the particular state, right? So this means that when you multiply this guy to this one, you end up with only the weight corresponding to that state, right? So you have 100 different states. You have 100 different weights, right? And then when you want to represent one of the states, say your first state, you're going to show 1 as the first entry. Everybody else is 0, right? These weights getting multiplied to this vector, only the first weight survives, right? And that guy comes out. This is your value estimate, right? If you are talking about the second state, then going to be one hot representation of your second state, which is 0, 1, 0, 0, 0, 0. And then the weights getting multiplied to this one, only the second weight comes out, right? So basically, every single weight that you have in this weight vector is the estimate of the value, right? And you initially start with some random choice, right? Or maybe you put it 0, right? And then gradually you keep on estimating, like what we did in tabular reinforcement learning, to change it, right? So this weight vector is essentially building your table. Do you see that? Right? So if your weight is if you set this weight vector to be something specific, then for that specific weight vector, if you want to know what is the estimate of the value for a state Sn, you need to just look at the weight number n, this vector, right? And that is your estimate, right? And as you keep updating that, that estimate gets better and better, right? Sounds familiar, right? This is basically what we did before. We initially started with no estimate, and we kept on updating them, right? So Now, one thing else is that the gradient of your value network, but in this case, the gradient is quite simple, right? Because looking at this expression, this value network or this value model, this is a linear multiplication, right? If you want to compute the gradient easily, just think of w and x to be scalars, right? What is the derivative of v with respect to w if everything is a scalar? It's x. It's going to be the same when you do vectorize, right? Just in a higher dimension, right? So the gradient of v with respect to the weights is going to simply be x, right? And that x is simply one hot vector in this case, right? Everybody's cool, yes? So you see what we are doing, right? So when we have a linear model, this is our gradient, the sample gradient of the network. That is the sample output of the network. And when we assume that the representation is done by tokenization. Questions? So if you got no question, then let's get this gradient and put it inside the loop that we found for training the function approximator. So if I want to just do the training, what I'm going to do, I'm going to update in this form, right? Say, for example, I'm doing temporal difference. So if I do TD, this is my estimate, right? My immediate reward plus the value of the next state given by the neural network or the model minus the value of this state, the current state that I am in. So this is the scalar multiplied with the gradient, right? Now, let me replace every single body here. So first of all, this guy, this value, we talked about this. The value of the particular state is going to be the corresponding weight, right? Everybody's cool? So this guy here, the value, when you put one particular state, the thing that is coming out is the weight corresponding to that state, right? Now, if you do it here, the value of your state st plus 1 is going to be the weight that is corresponding to that st plus 1, right? And I show that weight with v hat of st plus 1 because I am thinking of the table, right? I would say the first weight is the estimate v hat of state 1, right? Second is the v hat of s2, and so on towards the end, right? You see this, right? If you don't see it, I can write it on the board. Everybody seeing that? Questions? So you see why I replace it with v hat here? That is the corresponding weight, right? There is no shame in asking. You know that, right? Everybody's cool, yes? Okay, so this one is also the same, right? This is, again, the corresponding weight of a state st, right? Which is the estimate of state st, right? So I am replacing these ones with the corresponding weight or the corresponding estimates. That is the whole entire thing. And this one is basically my representation, which is a one-hot vector, right? Now, if I do this update, after multiplying this scalar with this vector, how does the vector look like? It's going to be one vector. Everything is 0. One of them is non-zero, right? And that thing that is non-zero is exactly this value, right? Everybody sees that, right? So now, that vector is going to get added to this weight, right? Which entry inside this weight gets updated then? Yeah? The entry corresponding to ST, exactly. That entry is going to get updated. Anyone else is just getting updated by 0, right? So I can throw them away. I don't need to update them anymore, right? So the thing that is happening is that only the weight of the corresponding entry, right? Corresponding entry to ST. If I assume that ST is being state n, right? Only weight of that state, Wn, is going to get updated. Anyone else is getting updated by 0, right? Everybody sees that, right? So that one is getting updated, and the update value that I get is this one, right? Everybody's cool, right? Now, what should I replace with what should I write instead of Wn? If you tell me, then I'm sure that you got what I said. What should be Wn? V hat pi of st. Great, so you're following. That's cool. Okay, this guy Wn is V hat pi of st, right? Everybody's cool, right? Because I have n different weights. I told you these are the V hats, right? And then this one is the V hat of Sn. Sn is st. So it's V hat of that particular state that I'm seeing, right? So what I can say Wn is essentially V hat of Sn, which is V hat of that particular state I am seeing at time t. And because of that, I am basically doing this update, right? This is my gradient descent update, right? Everybody's cool, right? And now this one, does it look familiar? Right? This is exactly the DD update we used to do, right? And that point of time, I didn't tell you we were doing gradient descent, right? I just told you, well, this is an estimate. This guy, then I just want to update incrementally, so I just add up with some alpha, and then I choose one alpha, right? And that alpha was essentially the learning rate, and this term that I was computing was actually the gradient of the dummy or linear model I used to approximate my value function. Everybody's cool? Questions? No question? Okay, so that one is tabular TD, and basically you can see that all of those other approaches that you have done, if you do the same thing here with neural network, when you put the state representation to be one hot vector, and you put your model to be linear, then eventually you're going to end up with the exact tabular form, right? But obviously what you know is that tabular is not working because this is not high capacity, right? So the linear model is not high capacity that it can capture all the details of the environment. So moral of the story is that tabular reinforcement learning is actually a special case of what we are doing, right? Is the special case of reinforcement learning with function approximation, right? And you can do better approaches by just developing more complicated or considering more complicated models for function approximation.